Okay, so in this video, we're going to continue talking about the extrema of a function. Hopefully we got through some of this in class. If we got further than what I think we will get, just kind of fast forward to where we left off. Okay, so hopefully in class, let me back up, sorry. The target for this video is students will determine absolute and relative extrema using the derivative process to determine the characteristics of functions. Okay, so hopefully we got through that first page and hopefully we got through the second page. At the end of the second page, we talked about the process for finding absolute extrema on closed intervals. Okay, so we're going to kind of do this process. So the first part of it was finding our critical values. Remember, our critical values are any values where our first derivative is 0 or undefined. Then we take each one of those values as critical values, we plug it into the main function as well as the endpoints. Okay, whatever yields the highest value is going to be our absolute maximum, and which one is our lowest value is going to be our absolute minimum. Okay, so we use something called the candidates test for this, and I'll talk about when we actually do it. Okay, so let's look at that first example. And the first example says, find absolute extrema of f of x equal to 3x to the fourth minus 4x cubed on the interval -1 to 2. Okay, so this is going to be the interval that we're working with, and of course this is a closed interval, which means we can apply absolute extrema from our mean value, not our mean value theorem, our extreme value theorem. Okay, so the first step in this process was in fact finding our critical values. So that's what I'm going to do first. So our critical values came from our first derivative. So let me get this on the page. This one's a pretty easy one. We get 12x cubed minus 12x squared. Okay. So once we get our derivative, our critical values come from where our derivative is equal to 0. Because remember, that's going to create those horizontal tangent lines. Of course, we want to also consider any undefined values. This one's not going to have any undefined values because of the fact that it's a cubic. So most of the time we'll be factoring, so that's exactly what I'm going to do in this problem. Factor out 12x squared is the GCF. X minus 1 is the end result, which means our x here is equal to 0. Remember, that comes from that guy right there. Okay, set it equal to 0 and solve. And our other x value is x equals 1. And that one comes from that right there. That was an unfortunate color choice with the background. Okay, so because 0 and 1 fall in the interval we're dealing with, remember that's that closed interval from the beginning. So because 0 and 1 are both in between -1 and 2, they're both what we call candidates to be the maximum or minimum. Let me get a different color. So both of these are candidates. Okay. Doesn't mean that they're going to be the max, going to be the min, but they're the possibilities. Because remember, our max and mins can happen at their endpoints, but it also can happen in the interior of our interval. And those are the 2 points within the interior that possibly could be maxes and mins. Okay, the next thing we do, so that's our first step. The next thing we do is we're going to take that 0 and that 1, and we're going to plug it into the main function. Okay, I like to use a table in this process. It just depends on what you prefer, but I often use a table here, so I'm going to create a table. And I'm not going to call this a T-chart because it's going to have an inner piece for my work. Outside is going to be x, the x that we plug in. The end result out here is going to be our f of x. And the equation that we're plugging in, I'm going to put in the middle. Now, part of the AP test, it's very important that you establish the equation in which you're plugging in. And this kind of takes care of that when we set up our T-chart this way. Okay, so all I'm going to do is take my candidates, 0, and what I'm going to do is I'm going to plug it back into the main function to get the corresponding y value. And that's going to be easy because when I plug in a 0, everything's going to 0 out, and my y value happens to be a 0. So that's one of the candidates. So at x equals 0, my y equals 0. When I plug a 1 in, again, I'm going to take f and I'm going to plug in 1. So 3 times 1 to the 4th power minus 4 times 1 cubed. Okay, 1 to the 4th, 1 cubed gives us 1. And we subtract those out, we get a -1. Okay, and then that's my step 2, was plugging in what we call the candidates. So this is my step 2 here. Now my step 3 comes from taking my endpoints. So now I'm going to take my endpoint of -1 and I'm going to plug it in, because it could happen that my max is at my endpoint or my min is at my endpoint. So -1 to the 4th minus 4 times -1 cubed. Okay. Depending on how large you write, go ahead and give yourself space within that inner piece. Okay. So if I plug it in, -1 to the 4th gives me +1, -1 cubed gives me -1, so I wind up having 3 minus -4, or 3 plus 4, which gives us 7. Okay. So right now, that's looking to be my max, but I still have one more value. I'm going to take that 2 and also plug it in. So not only are we plugging in our candidates, but we're also plugging in our endpoints as well. Okay. So f of 2, plugging in, we get 3 times 2 to the 4th minus 4 times 2 to the 3rd. That's a little larger calculation, so I'm going to take an additional step. So 2 to the 4th gives us 16. 16 times 3 will give us 48 minus 4 times 8, which would give us 32. If we subtract those, 16. And what this means is that I have a maximum, or actually I'm going to put absolute max. Remember, we can use AB for short, for absolute abbreviation. So I have an absolute max of, and the maximum value, remember, is the y value. So the highest value on here is 16. So I have an absolute max of 16, and it occurs at x equals 2. Okay. My absolute min, if I look on all my values, the lowest value is -1, so I have an absolute min of -1, and this is occurring at x equals 1. So on your AP exam, if you get into the habit of writing out that statement, absolute max of 16 at x equals 2, it kind of covers both, because sometimes the question could ask what is the maximum. It could also ask where the maximum occurs. So if you just write both of them, it kind of saves you some trouble of not completely answering the question. So I always write it out like that. Okay, so the second example on here is a different type of function. So we have part cubic, part linear. So I'm just going to jump in and start my process. So first step is, of course, taking the derivative to get our critical values. And I get 2 minus 2/3 times 3 gives us 2x. And when I subtract 1, I get a -1/3. Okay, so I'm just going to rewrite it really quickly, just like we've done in the past. So I get that. Now, because I have an x in my denominator, I have an undefined value. But that undefined value is, in fact, a critical value, because the point, or the definition of critical values, is where our derivative is equal to 0 or where it's undefined. So that right there, x equals 0, is going to make this equation undefined. So that's going to be one of my critical values. But I also want to set it equal to 0 to see if I have any more. So solving this, I'm going to move that fraction over the other side to make it positive. I'm just going to cross multiply really quickly. So 2 equals 2 cubed root of x, which means 1 equals the cubed root of x, which means if we cube both sides, x gives us 1. Okay. So I have a critical value of 1. I also have a critical value of 0, because 0 is where our derivative is undefined. Okay. So then I'm going to set up my candidates test. Okay, so that chart that we created is what we call the candidates test, and I'm sorry I did not say that earlier. But this entire thing, you might want to make note of it. When we do this process, we call that the candidates test. And on an AP exam, that serves as justification. Okay? So that's kind of a nice thing for us. Our work is our justification in this type of problem. Okay, so I'm going to set it up. So remember, we're going to start with x. Give myself some room. Our f of x is going to go in the middle. Important that you establish the equation you're plugging into. It was 2/3. Give myself some room just in case. And then x equal, or f of x. So I'm going to start with my critical value of 0. That's going to be an easy one because f of 0, we can clearly see, I don't really need to do the calculation, so I'm going to plug a 0 in here. So that's kind of one of the beauties, like if you put the equation at the top in the middle, you don't really have to show your work if you can do it really quickly, but it establishes the equation that you're plugging into. Okay, so that's my first critical value. If I take 1 and I plug it in, so f of 1 equals 2 to the first power minus 3 times 1 to the 2/3. Now 1 to any power is 1, so 1 to the 2/3 would give us 1. So we'd wind up with 2 minus 3, which gives us negative 1. Okay. So then after that, now that I've done my step 2, now it's time to look at my endpoints. So I'm going to take negative 1 first and plug it in. So you're not really plugging in everything, every point in between your interval and here. You're really just plugging in the critical values. Okay, so if I take that, 2 times negative 1 is going to give me negative 2. Negative 1 to the 2/3, remember that's negative 1 squared. 1 cubed root of 1 is 1. So that winds up being negative 2 minus 3, so negative 5. And then of course my last one, and I get, my last one is 3, because that's my other endpoint. So f of 3 equals 2 times 3 minus 3 times 3 to the 2/3 power. Okay. So I'm going to do some calculation really quickly because that one looks a little bit more complicated. So 3 not equals there, pardon me, minus 3, and we wind up getting the 3rd root of 9. So 6 minus, I don't know what the 3rd root of 9, so I'm going to leave it as the 3rd root of 9. Okay, so if we think about it, the 3rd root of 8 is about 2, so I'm going to estimate that to be about 2. So I wind up getting 0 there, or either that or 6 minus a small number. And that's not really going to give me, it's going to actually wind up giving me a negative number if we think about it. 0, and it's going to be less than that. And in fact, when I put this in the calculator, I think I got negative 0 point. Let me double check that really quickly. 0.24. Okay, so thinking of that and looking at all those values, what that means for me, let me get a different color, that I really have a max of 0 at x equals 0, and I have a min of negative 5 at x equals negative 1. And it'd probably be a good thing to put absolute here. Okay, sorry about that. Okay. If we actually look at the graph of this one's kind of a pretty interesting graph. I'm just going to sketch it out really quickly. I sketched it out on my calculator. That's why I know what it looks like. But it actually looks like this. And if you see right there at the 0, we have a cusp. Okay, and that's where our derivative was undefined, if we go back to where we started at the beginning. It's kind of interesting to see that graph, to see what's going on. Okay, the last example I'm going to do with you is this example 2, and then I'm going to ask that you actually finish out the next example before you get to class the next day. Okay, so this next one's kind of a little interesting, because it says, the question asks, find the smallest possible slope of the tangent line. So we are actually looking for the smallest possible slope, which means the question is truly asking for the minimum slope. And that's kind of a weird thing to think about. It's going to kind of affect what we do, because if I want to find the minimum slope, that means I'm really taking the derivative of the slope equation. So we're actually going to be working with the second derivative, because if I want to find the minimum of the slope, I first need to get the slope equation. So I'm going to start there. So our slope equation, we know from everything we've done in here, comes from the derivative. And a weird thing about this problem is it didn't give us an actual interval to look at. But if we look at our derivative equation, remember this is the slope equation. it's a quadratic, which means it's a quadratic facing up, which means the minimum is the absolute minimum of this function. So we don't really even have to worry about the endpoints. We don't need endpoints to kind of see where we start and where we stop. But I want to find the minimum of that equation. And what that means for me is I'm going to actually be taking the derivative of the slope equation, which happens to be my second derivative here. And that's where I'm going to get my critical values from. Okay. Set that equal to 0 to get critical values. Factor, we get 2x minus 1, which means x is equal to 1/2. And it wants to know what the actual minimum slope is. So I'm going to actually have to take that and plug it back in to the slope equation, which is that equation right there. So really we're plugging in to the derivative. Again, the only reason we are going to only plug this value in is because this is a quadratic equation facing up, so the vertex is our minimum here. And it is the absolute minimum. So I wind up getting, what, 6/4 for that, minus 3 plus 1. So 3/2. Sorry, plus 4, not 1. So that winds up giving us plus 1. I think that's where I got the 1 from. And if we think about that, that gives us a 5/2. So the smallest possible slope on this equation happens to be 5/2. So coming into class tomorrow, if you could please look at this one, see if you can actually try to do this one. Okay, see if you can kind of understand it based on what we did on the previous problem, and then come in with questions. So if you need anything, come into class and ask in the morning.